TaleForge. In this video I want to show you how I implemented 10,000 skin mesh renderers using Rukhanka, VContainer, Polyview and a few other assets, all in Unity ECS. So let's dive in. First of all, let's review the scene settings. The main camera is configured very basically, with post-processing disabled and a solid color set as the background type. Nothing fancy. I also have an animator added because the camera is animated in the timeline. Next, the directional light. I have increased the intensity to 3 because my scene was very dark, especially at a great distance. I disable shadows for better performance. The event system was created automatically when I created a canvas. Now let's take a look at the canvas. It is overlay canvas with some basic settings for full HD. I created a slider here, importantly with values ranging from 0 to 10 because I assumed a transition from 0 to 10,000 units in increments of 1000. Of course, whole numbers must be checked. Then I prepared unit text, change font size and write some basic input text. Here we have flow control buttons, dance, idle, and run. I mostly use them for debug purposes to check if animations are working properly. Then I use this logic in the timeline signals. Okay, other things will be discussed later in this video. It's time to implement our animating object prefab. First of all, let's talk about the assets. I use the low poly magician model, which is highly optimized character with an acceptable number of triangles, around 3000. I also use the free low poly human RPG character animation asset for the hide and run animations. I would highly recommend it for prototyping. And the last one is human dance animations free, which I obviously use for the dance animation. So let's go to the Unity. First of all, I added Animator Controller with Magician character avatar. Let's have a look at the animator settings. As you can see, I have prepared 3 states: dance, idle, and run. I have connected the transitions and assigned the appropriate transition state between them so that it is possible to move from one state to another. In addition, I have disabled exit time to make the transitions smoother. Later, I will modify the animator parameters from the ECS code using Rukhanka. Okay, let's go back to the animating object. It is important to set culling mode to the cull completely. It is important optimization, which will let us spawn more units. Last thing to do, let's add rig definition affairing. It is a Rukhanka class, which will allow us to configure animation and parse it from mono to ECS world. Here we also want to optimize animations. Let's disable built-in movement and set animation engine to GPU. This will significantly improve the game's performance. Also, let's set bone entity stripping mode to automatic. It will destroy any unnecessary bones and improve performance because we'll have less entities in the subscene. Alright, we set up animations. Now it's time to optimize the mesh. For this purpose, I use the Polyview package, which allows us to significantly reduce the number of triangles used in the model without distorting the character itself. So let's select the Consider Trident option, as our magician model is lower in the hierarchy. As you can see, with Polyview, I can configure automatic LOD and immediately perform optimization on the mesh for specific groups. I created 3 levels here with the specific parameters, taking care to preserve borders, UV seams, regard curvature, use edge sort, and recalculate normals. This allowed me to perform satisfactory optimization without distorting the model. In result, I achieved 1.1 million triangles for 10,000 skin mesh renderers. After creating the LOD, a Polyview object was created. If we leave it in this form, our performance will suffer, because all these objects will be converted to entities. Therefore, let's use the baking only entity offering component on this group, as it will significantly improve performance. In my case, this resulted in a 50% performance gain. A lot of calculation on ECS local transforms were eliminated this way. While we are on the subject of optimization, let's move on to mobile RP asset. Here, I disable HDR and reduce the render scale to 0.8. In addition, I enable the Fidelity FX upscaling filter so that the quality of the displayed image would not suffer. The last thing I had to do was create the RukhankaDeformation lead shader. Deformation modules are necessary for skin and mesh renderers to work properly in ECS. The flow is as follows. I copied the original materials and added the part concerning Rukhanka. I have to add RukhankaDeformation group and inside it create the format mesh index and deformation params for motion vectors with hybrid per instance selected. Here I also added a simple color multiplication so that I could modify it from the editor just like the original material. And I checked allow material override. Fortunately, nothing complicated. I did the same in the second material. Finally, we have our prefab prepared. This is time for swim.
Bonjour, mes amis.
Let's start with UnitSpawner component data, which will contain spawn-related data. It is a simple struct that stores entity prefab, a bool flag spawn, and int units to spawn. Of course, it implements the iComponent data interface. Next, I have prepared UnitSpawner offering, the purpose of which is to convert mono prefab to ECS via UnitSpawner Baker. In Baker, I mark the entity as renderable, will not be moving it, so there is no need to use dynamic. I also prepared an enum called Rukhanka Showcase Animation State with 4 states: None, Dance, Idle, and Run. We'll need it in a moment in component data. Next, I created a structure that stores information about the currently playing animation, UnitAnimation component data, with a public field called Rukhanka Showcase Animation State. This component should be baked, that's why I prepared UnitAnimation offering and Baker, so just call add component and set the state to none. Last iComponent to create is unit component data with 2 parameters, public Rukhanka Showcase Animation State and Fast Animator parameter, so our current animation state and animator parameter. We created all these classes so that we could, first of all, instantiate characters and secondly, animate them using Rukhanka. As you can see, I created UnitSpawnerSystem. This iSystem is marked as Bells compile. We don't use any managed types. In onCreate, I need to assign unit query so that I can destroy old entities when spawning new ones. I also need to add a require for an update for both our singleton unit spawner component data and entity command buffer simulation group. In onUpdate, I call systemapi.getSingleton unit spawner component data, and if the spawn flag is not set, I terminate the operation. However, when the spawn flag is true, I change its status to false and continue executing the code. Also, I get entity command buffer, of course, as parallel writer. If unity query is not empty, I clear the old entity using unit destroy job. It is important to pass unit query because we want to do operations only on the units. Of course, I use schedule parallel. Also, I call jobHandle.complete to wait for the job finish. Let's have a look at job implementation. I am simply destroying entity via ECB parallel writer with parameters sort key and entity. Okay, let's go back to the onUpdate method. If units to spawn equals 0, let's return. Now I use a syntax that is highly efficient. Using var entities equals new native array entity UnitSpawner component data.units to spawn allocator.temp job. Now I can refer directly to the state.entityManager.instantiate, pass the prefab and the array, and spawn as many objects as I need in a single operation. Next, I create a new job, new animating object configuration job, and pass square from the number of units, entities, and ECB parallel writer. In this case, I use iJobParallel4, so I have to pass the array length, batch count, and state.dependency. Finally, I wait for the operation to complete. Here I have getEntity command buffer code, in this case with parallel writer. Okay, let's have a look at the animating object configuration job. As I said, it is iJobParallel4, so I had to implement public void execute int index. It is important to note that entities need to be marked with read-only attribute because we will not modify them in the job. Inside job, I use simple indexing logic to get units in square, with a small shift, but it doesn't matter for showcase. Next, let's add a new unit component data with an iLoop parameter and set local transfer component from our entities array at a position of a new float x, 0, z multiplied by 2. Multiplying by 2 will give us some space between spawned entities. That's it. It's time to implement our UnitAnimationSystem. Here we need to create unit query and fast animator parameters for dance, idle, and run. Of course, build unit query in the onCreate, as well as add require for update for necessary component data. Next, in the onUpdate, we want to check if our state is none. If so, return. So we can switch expression animator parameter. Depending on the status, we return the right fast animator parameter. Then let's create new unit animation job, pass state and fast animator parameter. Don't forget to pass ECB parallel writer. At the end of this method, we want to reset animation state to none, so system will not be updated any longer. In the unit animation job, in the execute method, I added animator parameters aspect, which is our most important element which will allow us to manage our animation. If the current animation state is not known, set the bool parameter to false for the previously played animation. Then set the current animation to play with the true parameter and assign the unit component data parameters. At the end, remember to set component via ECB parallel writer. Okay, so it's time to create our messages. Rukhanka showcase animation message with parameter Rukhanka showcase animation state and Rukhanka showcase spawn message with int units to spawn. So let's implement our communication. In the Rukhanka showcase system, we mainly use VContainer, which allow us to implement subscribers to previously created messages. Of course, this requires communication to take place at the managed level, hence system base. I use disable auto creation attribute to manually register the system and inject dependencies. I will skip the full explanation of the VContainer subscribers and also publishers which are later in the video. I have a video on the channel that explains this, link in the description. So I will go straight to the handles. In the first handle, we need to change animation state and set singleton when event occurs. In the second one, we need to set spawn flag to true and assign units to spawn to the component data. Then also call set singleton. And that's it. Finally, we can move to the Rukhanka showcase model, which mostly have serialized feeds and getters. Inside it, I have put custom public event action slider pointer up. This event is invoked in the slider pointer up event trigger method, which is used by event trigger in the Unity editor. I didn't want every slider movement to cause a state change, so the entities are only destroyed and spawned when the slider is released. So pointer up. Great, so let's go to the Rukhanka showcase service. This class has two publishers for our messages, and also some public methods. Change state, which publish Rukhanka showcase animation message with new state. Calculate units with the following input parameters: a float value and an int slider base value, so we can calculate how many units need to be spawned. Set unit text, I think this is self-explanatory, and spawn units, which publish spawn message with numbers of units to spawn. So we have our logic, our data. Now we need to communicate it all. In the Rukhanka Showcase Presenter class, which implement iInitiateBoo and iDisposable interfaces, we have to prepare constructor for injecting service and model classes. In the initialize and dispose methods, we want to add and remove listeners. Also, during the initialization phase, we want to set unit text to 0. So let's have a look at the methods. Dance, idle, and run are very straightforward methods. Just call change state and pass right parameters. Set unit text reacts to change in the slider. With each change, the units must be recalculated and the view updated. The spawn unit function is executed on pointer up, spawning the required number of units according to the value set on the slider. Finally, we can move to the Rukhanka Showcase Lifetime Scope, where registration magic occurs. So, as usual, we register the service as scope, the presenter with entry point for interfaces, and the component based on getComponent. Finally, we must remember to register the Rukhanka Showcase system in default world, so that we can inject dependencies. At the end, let's change LOD group.crossfade animation duration to 0.3. The last class is for timeline. It allows us to handle custom actions. I will scroll slowly so you can see logic inside it. However, it is nothing fancy. I will leave it as it is, but the word debug doesn't fit in this context. Originally, this class was supposed to do something else, so its name could be refactored to simply Timeline Controller. It's time to return to Unity. In Rukhanka Showcase Scope, I added two scripts, Model and Scope. In the model, I moved the references to our buttons, slider, and text, and set the base value for the slider to 1000. Below, I added the script necessary for communication with Timeline. Debug Timeline Controller, with a reference to the camera and a black target color. At the very bottom, we can see Signal Receiver, which was created after creating signal emitters in Timeline. It is a component responsible for listening to signals and executing our custom logic. To optimize animation, I created an animation frustum culling object and added the animation culling config component provided by Rukhanka. Animation calculation can be disabled for the entities whose renderers are not visible to the camera. Quite useful feature, right? Okay, it's time to discuss Rukhanka Showcase subscene. I created two objects, UnitSpawner, in which I attach UnitSpawner offering plus pass animating object, and UnitAnimation, where I added UnitAnimation offering component. Next, as you can see, I created a playable director that automatically plays on awake with the wrap mode set to hold. Okay, so let's open it in the timeline. I would like to tell you a little more about it. I perform most of the operations on the camera, changing its position and rotation. As you can see, there are quite a few keys here that contains information about the current data. Similar in the directional light, we have a rotation. I changed the angle to better illuminate the characters on the scene. I also prepare some signal emitters, so I can invoke custom logic during timeline sequence. It allows me to change slider value, so spawn more units, change background color, or change animation state. And it's also simple. Just select reference, our timeline script, choose method and pass parameter if necessary. Okay, it's time to show, once more, the final result. Enjoy! I would like to invite you to support us on the Patreon, where you can get the exclusive code, all models, materials or code used in this series, and access to early available content. Link in the description. Thank you for your time, I'm glad you are with us and our community is growing. See you soon in the next video.